18 of the 31 vital signs scientists use to measure Earth's health just broke records, all in the wrong direction. Over 15,000 researchers from 184 countries signed the same letter, not a petition, a warning. They're watching tipping points line up like dominoes. We'll go through a rainforest turning into a gas leak, ice sheets that could drown entire cities, and a sun that will eventually end all life on this planet. If you want more videos like this, subscribe and hit like. It helps more than you think. Now, let's begin. It started with a letter, not a government memo, not a news headline. A letter signed by over 15,000 scientists from 184 countries, sent to every major institution on the planet. The message was simple: we are running out of time. To understand why that letter mattered, you have to understand who signed it. These weren't activists or politicians. These were the people who spend their lives measuring things: ocean temperatures, ice thickness, carbon levels, species counts, data people, numbers people, people trained to stay calm and let the evidence speak. And the evidence made them panic. The letter went out in 2017. It built on an earlier warning from 1992, when 1,700 scientists tried to sound the alarm the first time. Almost nobody listened. So they came back, this time with 8 times as many signatures and a much darker message. The systems that keep Earth stable were no longer just under stress. They were beginning to crack. What exactly were they seeing? Think of Earth as a living machine. It has systems that regulate temperature, clean the air, cycle water, and support every creature alive. These systems don't fail all at once. They fail the way a bridge fails. Slowly at first, a bolt here, a crack there. Then one day, without dramatic warning, the whole structure gives. Scientists had built a list of 31 measurements they called planetary vital signs. Things like global average temperature, glacier volume, forest coverage, ocean acidity, and sea ice levels. These were the equivalent of a doctor checking your pulse, your blood pressure, your oxygen levels. And in the years leading up to that letter, those vital signs kept moving in the same direction. Down. Here's the part that should grab your attention. By 2021, a follow-up study confirmed that 18 of those 31 vital signs had hit their worst readings ever recorded. 18 records, broken simultaneously, all pointing toward collapse. Now, scientists are careful people. They argue about data. They question each other's methods. So when 15,000 of them agree on something, that agreement itself is the signal. It means the evidence is so clear, so loud, so consistent across every country and every measurement type, that denial becomes scientifically embarrassing. But here's what made this letter different from all the others. The scientists didn't just describe the problem, they attached a timeline. They said certain systems were approaching a threshold, a point of no return, after which no amount of human effort could reverse the damage. They called these thresholds tipping points, and they said several of them were dangerously close. Picture a glass of water sitting at the edge of a table. You can push it a little. You can even tip it halfway. But there's a moment, one specific angle, where gravity takes over and nothing you do can stop it from falling. That's what a tipping point is. Earth has dozens of them, and scientists were watching the glass slide closer to the edge in real time. The letter also included something unusual for a scientific document: urgency, raw, direct urgency. They wrote that civilization was at stake, that the window to act was narrowing fast, that the changes needed were structural, global, and immediate. And then most of the world moved on to other news. The scientists didn't stop watching. They kept measuring. And what they found in the years that followed made the 2017 warning look almost optimistic. Because the vital signs didn't stabilize. They kept falling. And one number, more than any other, explains why. 43%. That's the share of Earth's land surface that humans have already transformed. And the story of what happens when that number keeps rising is where things get deeply uncomfortable. Most people check their health without thinking about it. You feel tired, you check your sleep. You feel sick, you check your temperature. Your body constantly sends signals that something is off, and those signals give you time to act. Earth works the same way. Scientists figured that out decades ago and built a system to track it. They call these measurements planetary vital signs. 31 of them. Each one tracks a different part of the global system. Together, they paint a picture of how healthy or how sick the planet actually is. Some of these are obvious. Global average temperature, sea level, Arctic sea ice coverage, the amount of carbon dioxide in the air. These are the ones you hear about on the news, but others are far less familiar, and in many ways, far more frightening. One vital sign tracks the total mass of freshwater stored in glaciers around the world. Another measures the total area of intact forest still standing on Earth. There's one that tracks the global population of marine mammals. Another follows the amount of dead zones forming in the ocean, places where the water has so little oxygen that almost nothing can survive. Each vital sign is like a single instrument in an orchestra. When one goes off key, you might not notice right away. When several go off key at once, you hear it. When 18 of them hit their worst numbers ever recorded in the same year, the whole orchestra is falling apart. Here's what makes that number so alarming. These are systems that took thousands of years to build, glaciers that grew over tens of thousands of winters, forests that evolved over millions of years, ocean chemistry that took geological time to balance, and they are now changing faster than at any point in recorded human history. Scientists use the word acceleration a lot. That word matters. A car going 50 miles per hour is fast. A car accelerating from 50 to 100 miles per hour while the brakes are failing is a different kind of problem entirely. Earth's vital signs aren't just moving in the wrong direction, they're speeding up. Take ocean heat as one example. The ocean absorbs most of the extra energy trapped by greenhouse gases. Scientists measure ocean heat in layers, from the surface down to the deep. In recent years, the ocean has absorbed more heat per decade than in any prior period on record. That stored heat doesn't disappear. It drives more powerful storms. It bleaches coral. It raises sea levels because warm water physically expands. Or take the loss of sea ice in the Arctic. When that ice shrinks, it exposes dark ocean water beneath. White ice reflects sunlight back into space. Dark water absorbs it. So less ice means more heat absorbed, which melts more ice, which exposes more dark water. Each step makes the next step worse. Scientists call that a feedback loop. The 31 vital signs exist precisely because no single number tells the full story. Carbon dioxide levels alone don't capture what's happening to biodiversity. Sea level rise alone doesn't capture what's happening to the jet stream. You need the whole picture. And right now, the whole picture shows 18 of those readings at record-breaking lows or highs, depending on which direction is dangerous. The fact that so many broke records in the same window of time tells scientists something important. These systems are connected. When one weakens, it pulls at the others. 18 records, all broken in the wrong direction. But one number, hiding in plain sight, explains how so much damage happened so fast. And it has everything to do with what humans did to the land itself. Stand somewhere quiet and look at the ground beneath your feet. Concrete, asphalt, farmland, or maybe actual soil with grass pushing through. Whatever you're standing on tells a small piece of a much larger story. Humans have physically transformed 43% of Earth's entire land surface. Roads, cities, parking lots, farms stretching from horizon to horizon, pastures where forests used to stand. 43%. That's nearly half the dry land on the entire planet, reshaped to serve human needs. To picture that, imagine the entire continent of North and South America combined. Then imagine wiping nearly half of it clean of every natural ecosystem that existed there, and replacing it with something built or planted by people. That's roughly the scale of what has already happened across the globe. Now ask yourself, what was there before? Before farms, those regions were forests, grasslands, wetlands, and savannas. These ecosystems weren't just scenery, they were machines. Forests pulled carbon dioxide out of the air and locked it into wood and soil. Wetlands filtered water and absorbed flood surges. Grasslands held topsoil in place against wind and rain. Every acre of natural land did invisible work that kept the planet's systems balanced. When those ecosystems get replaced, that work stops. The carbon stored in the trees gets released. The soil loses its structure and begins to erode. The water cycle in that region shifts, sometimes making nearby areas drier, sometimes making them flood more easily. And the species that live there either move, adapt, or disappear. Scientists put a specific number on the danger zone: 50%. Researchers believe that if humans transform 50% or more of Earth's terrestrial surface, it could trigger irreversible ecosystem collapse across interconnected regions. The systems are already stressed at 43%. 7 more percentage points could push multiple ecosystems past a breaking point simultaneously. And here's the part that makes this feel urgent right now. That number is still climbing. Every day, more land gets cleared for agriculture, more forest gets cut for development, more wetland gets drained for construction. The rate of transformation has slowed in some regions, but globally the trend keeps moving in the same direction. What's especially alarming is the loss of what scientists call natural carbon sinks. These are places, mainly forests and wetlands, that absorb more carbon than they release. They act like giant sponges for the greenhouse gases humans keep pumping into the atmosphere. Destroy those sponges, and the gas has nowhere to go. It stays in the air. It traps more heat. There's also the soil story, and most people haven't heard it. Healthy natural soil is one of the largest carbon stores on Earth, holding more carbon than all the world's forests combined. When land gets plowed and exposed repeatedly for agriculture, that carbon oxidizes and escapes into the air. Billions of tons of it, silently, invisibly. 43% transformed. Systems already wobbling. 7 percentage points from a threshold that scientists call a serious danger marker. The land transformation story gets even harder to look at when you zoom in on one specific region. A place that produces 20% of the world's oxygen. A forest so large it creates its own weather. And right now, that forest is doing something that no one expected this soon. Something that completely flips the role it was supposed to play. Picture a wall of ice the size of the entire state of Alaska. Greenland's ice sheet covers over 650,000 square miles. In some places, it's almost 2 miles thick. It's been sitting there, locked in place, for hundreds of thousands of years. Scientists knew it was melting. That part wasn't the surprise. The surprise was the speed. And something else, something far more unsettling hidden underneath the ice itself. Here's how glacial melting works at the basic level. As temperatures rise, the surface of the ice sheet warms. Ice melts. Water trickles down through cracks in the ice called moulins, essentially drain holes that go all the way to the bedrock below. Once that meltwater reaches the base, it acts like a lubricant between the ice and the rock underneath. And when ice slides on water instead of grinding on rock, it moves faster. A lot faster. Think of it like this. Imagine pushing a heavy box across a dry concrete floor. You have to work hard. Now pour a thin film of water under that box. It glides. That's what meltwater does to glaciers. It makes billions of tons of ice flow toward the ocean at a rate that was never part of the original calculations. But the domino part, the piece that keeps scientists up at night, is the feedback loop locked inside the ice sheet's own shape. Greenland's ice sits inside a bowl. The center of the island is actually lower than the edges, like a giant shallow dish. As the edges melt and thin, the center of the ice sheet sits lower in the atmosphere, where temperatures are naturally warmer. So as it melts, it descends to warmer air, which melts it faster, which lowers it further, which puts it in even warmer air. The ice is melting itself into a worse position, automatically, with no extra push from the outside. Scientists calculate that if Greenland's ice sheet melts completely, global sea levels would rise by roughly 20 feet. 20 feet. The Empire State Building is over 1,400 feet tall. But even 5 or 6 feet of sea level rise would permanently flood some of the most densely populated coastlines on Earth. Miami, Mumbai, Bangkok, Shanghai, cities that hold hundreds of millions of people, most of them built on land that sits barely above current sea level. And here's the critical concern researchers keep raising. Every major ice system has a tipping point. A temperature threshold beyond which the ice commits to melting, no matter what happens next. Cross that line and the sheet enters an irreversible decline. Humans could stop all emissions overnight and the ice would still go. Scientists are actively debating whether Greenland has already crossed that line. Some models say yes, others say it's close but not yet reached. That debate is still open. But Greenland is only one piece of the picture. And compared to what's sitting at the other end of the planet, Greenland's ice sheet is almost modest. The ice system in the west of Antarctica holds enough frozen water to raise global sea levels by nearly 11 feet on its own. And it has a structural weakness built right into its geography that makes it behave very differently from any other ice on Earth. That story changes everything about how we think about the timeline. Scientists gave it a name, Hothouse Earth. 2 words that carry an enormous amount of meaning packed into them. The hothouse scenario is a specific trajectory the planet could follow if certain climate systems tip beyond their thresholds. And the terrifying part about it isn't just how hot it gets. The terrifying part is who's in control once it starts. Right now, humans are the main driver of climate change. Burn more fuel, temperatures rise. Cut emissions, the rise slows. In theory, we hold the wheel. The hothouse path is the one where we lose the wheel entirely. Here's how it happens. Earth's climate isn't controlled by one system. It's a web of interacting systems. Forests, ice sheets, ocean currents, permafrost, atmospheric gases. Each one influences the others. When they're all stable, they keep each other in balance. When one starts to fail, it puts stress on the neighboring systems. Scientists identified a set of these interconnected systems and gave them a name. Tipping elements. Each one has a threshold. Push it past that threshold, and it shifts into a new state on its own, releasing stored carbon, absorbing less heat, or both. And that shift pushes the next tipping element closer to its own threshold. That's the cascade. And once it starts, it feeds itself. Imagine a line of dominoes set up with careful spacing. You tip the first one, it hits the second hits the third. At some point, the dominoes are falling faster than any hand could possibly stop them. The hothouse scenario is what happens when Earth's own natural systems become the dominoes, and human activity has already pushed the first one. The researchers who defined this scenario published their findings in a major scientific journal. Their conclusion was stark. If global temperatures rise roughly 2 degrees Celsius above pre-industrial levels, which is about 3.5 degrees Fahrenheit, the cascade of tipping points might become unstoppable. The planet could continue warming on its own, driven by feedback loops, until temperatures stabilize at a level roughly 9 degrees Fahrenheit, higher than before the industrial age. 9 degrees Fahrenheit sounds manageable to a lot of people. It's the difference between a warm spring day and a summer afternoon. But when you apply that shift to the entire planet's average temperature, the effects are catastrophic. Regions that currently grow most of the world's food would face regular droughts or extreme heat that makes outdoor farming lethal. Sea levels would rise enough to displace hundreds of millions of people. Weather systems would become fundamentally unpredictable. The most unsettling detail is this. Once the cascade starts, the heat continues rising even if every human emission stops. Permanently. The natural systems take over the job of warming the planet themselves. Scientists are careful to say this pathway is a risk, not a certainty. The exact temperature threshold for the cascade is still debated, but the mechanism itself is solid. The physics is real. The feedback loops exist, and several of those tipping elements are already showing stress. The Greenland ice sheet, the Amazon rainforest, the West Antarctic ice sheet, boreal permafrost across northern Canada and Siberia. Each of them is already responding to warming in ways that were predicted, but arriving faster than models expected. The hothouse isn't something that happens far in the future. The early steps are already underway, and one of the most dramatic examples of that is happening right now in one of the least expected places. A place most people think of as a life-giving system is quietly becoming something else entirely. 9 degrees Fahrenheit. On a thermometer, that looks small. Move your finger slightly up the scale and you've covered it. But apply that number to the average temperature of an entire planet, and it rewrites geography. To understand what 9 degrees actually means at a global scale, look at what a single degree has already done. Earth's average temperature has risen about 2 degrees Fahrenheit since the Industrial Age began. 2 degrees. That's enough to intensify hurricanes. That's enough to expand deserts. That's enough to cause 100-year floods to happen every 10 years in some regions. 2 degrees has already reshaped weather patterns across entire continents. Now multiply the impact of those 2 degrees by 4.5. That's the 9-degree world. Scientists have modeled this scenario using the most advanced climate simulations available. The results reshape the map. Large portions of the Middle East and South Asia would experience outdoor temperatures that exceed what a human body can survive without air conditioning. During peak summer heat, the combination of temperature and humidity in those regions would make it physically impossible for the human body to cool itself. You could stand in the shade, completely still, and your core temperature would keep rising. The tropics, the equatorial belt that currently holds some of the highest biodiversity on Earth and feeds billions of people, would largely become zones of lethal heat for parts of the year. Move toward the coasts. Sea level rise in the 9-degree world would likely fall somewhere between 15 and 30 feet above current levels. Though the exact number depends on how quickly ice sheets in Greenland and Antarctica collapse. Even the low end of that range drowns cities. New York, London, Tokyo, Mumbai, Lagos, all of them would face flooding that makes current storm surges look manageable. The flooding wouldn't come and go with the tide. It would be permanent. Inland, the story shifts from too much water to too little. The western United States and large parts of Africa would face drought conditions far beyond anything in modern recorded history. The soil would dry, crack, and lose its ability to hold crops. Rivers fed by glacier melt would shrink and eventually disappear. The Colorado River, already stressed, would face a future where the snowpack that feeds it largely stops forming. Extreme weather events would change in character. Storms would carry more moisture because a warmer atmosphere holds more water vapor. When they release that water, they release it all at once, not in steady rain, but in downpours that overwhelm drainage systems built for a different climate. Here's the part of this that many people don't immediately grasp. The 9-degree world doesn't replace the world we know, it arrives on top of it. The infrastructure built for the current climate, bridges, roads, power grids, hospitals, water treatment plants, all of it gets stress tested by conditions it was never designed to handle. A bridge built to manage a 100-year flood gets a 100-year flood every decade. A city drainage system built for 3 inches of rain in a day gets 6. A coastal desalination plant built just above current sea level gets submerged. The cost of that mismatch, rebuilding, relocating, or losing entire cities, would be unlike anything human civilization has managed before. And the 9-degree world isn't the ceiling. It's a midpoint in the hothouse trajectory. Some models project even higher stabilization temperatures if the most extreme feedback loops activate. But before the world reaches those temperatures, something else has to go wrong first. Something closer to home. something green and enormous and already in the middle of quietly switching sides. The Amazon rainforest is roughly the size of the entire continental United States. For millions of years, it performed one of the most important jobs on Earth. It pulled carbon dioxide out of the air and locked it into living wood, roots, and soil. Billions of tons of carbon stored and held year after year. Scientists called the Amazon a carbon sink, a place that absorbed more carbon than it released. One of the planet's most critical tools for keeping greenhouse gases in balance. That role is now at risk of reversing. Research published in recent years shows that large sections of the Amazon, particularly in the eastern and southeastern parts, are already releasing more carbon than they absorb. The forest that was supposed to slow climate change is beginning to add to it. Two forces are working together to cause this. The first is deforestation. Huge areas of the Amazon have been cleared for cattle ranching and agriculture over the past several decades. When trees are burned or cut, the carbon stored inside them escapes directly into the atmosphere. Over decades, this has degraded enough of the forest to shift the carbon math in those regions. The second force is climate change itself. The Amazon creates its own rainfall through a process scientists call a biotic pump. Trees pull water from the soil and release it through their leaves as water vapor. That vapor rises, forms clouds, and falls back as rain, which feeds the trees, which release more vapor. The forest essentially generates its own weather system. But as the forest shrinks, the cycle weakens. Fewer trees mean less vapor, which means less rain, which stresses the remaining trees. And a stressed forest burns more easily. The dry seasons are getting longer and more intense. Each year brings new record fire seasons across the region. Scientists have identified a specific threshold they're watching closely. If deforestation reaches somewhere between 20 and 25% of the Amazon's original area, the moisture cycle could collapse across the whole basin, even in regions that were never cleared. The remaining forest would begin dying back on its own, releasing its stored carbon in a process that would take decades and could release amounts comparable to multiple years of total global human emissions. The eastern Amazon has already crossed a regional version of this threshold in some models. Picture a sponge that's been squeezed until it can't hold water anymore. It goes from cleaning up a mess to making the floor wetter. That's the transition researchers are watching happen in real time. And the scale of carbon involved is staggering. The Amazon stores an estimated amount of carbon roughly equal to 20 years of current global fossil fuel emissions. If even a fraction of that gets released over the coming decades, it adds a massive, self-sustaining push to warming that has nothing to do with what humans decide to burn next Tuesday. Scientists are careful to say the full Amazon tipping point hasn't been crossed yet, but the signals in the eastern region are clear enough that a team monitoring the data published a paper describing the situation as a critical transition already in progress. The forest that was supposed to buy humanity time is running out of it. And the Amazon isn't the only massive carbon store on the edge. Beneath the soil of northern Canada, Alaska, and Siberia, something far older has been frozen in place for thousands of years, and it's thawing. Permafrost sounds like a geology term, something distant and academic, but what it actually is and what it's releasing right now is one of the most urgent stories in climate science. Permafrost is ground that has stayed frozen continuously for at least 2 years. In places like Siberia, northern Canada, and Alaska, it's been frozen for thousands of years, in some regions for tens of thousands. This isn't just frozen dirt. Over millennia, dead plants, animals, and organic matter got buried in this ground and locked in place by the cold before they could fully decompose. The result is a massive underground storage of ancient organic material, holding roughly twice as much carbon as the entire atmosphere currently contains. All of it frozen, all of it waiting. When permafrost thaws, microbes in the soil wake up and start breaking down that ancient organic material. As they do, they release carbon dioxide and methane directly into the atmosphere. Methane is a greenhouse gas roughly 80 times more powerful than carbon dioxide over a 20-year window. And permafrost holds enormous quantities of it. Here's why this story is different from other warming risks. With fossil fuels, humans make a decision every time they burn them. Someone decides to fly a plane, run a factory, or drive a car. Those emissions can, in theory, be reduced by changing those decisions. Permafrost thaw doesn't work that way. Once the ground warms enough to melt, the process is self-sustaining. The microbes keep working. The gas keeps escaping. There's no valve to turn off. Scientists have mapped the permafrost zones across the Arctic, and the measurements coming back from those regions are alarming. Ground that was frozen solid decades ago is now soft enough to walk through in summer. Entire hillsides are collapsing in Siberia because the frozen ground that held them in place is melting. Homes and roads built on permafrost in Alaska and Canada are tilting, cracking, and sinking as the earth beneath them shifts. The visual that captures the scale best is this. Scientists have found lakes across Siberia bubbling with methane, sometimes in such concentration that researchers can light the surface of the water on fire. The ground is exhaling gas that has been trapped underground since the last ice age. Nobody knows the exact rate at which permafrost will thaw globally. The uncertainty is enormous and deliberately honest. Scientists have wide estimates because the variables are complex. How warm does it get? How fast? How deeply does the heat penetrate the soil? What's the ratio of methane to carbon dioxide released? What scientists do agree on is that current warming trends are thawing permafrost faster than most models predicted a decade ago. The gas is coming out sooner and in more places than expected. The boreal permafrost zone covers more land than the continental United States and Europe combined. Even a fraction of that thawing and releasing its stored carbon would add a significant, unstoppable push to global warming. Scientists call this a sleeping giant, and the giant is beginning to stir. The permafrost story is about ancient carbon escaping from the ground. But there's another type of loss happening simultaneously, one that doesn't happen underground. It happens out in the open, species by species, quietly and steadily, in a pattern that has only happened 5 times in the last 500 million years. 5 times in Earth's history, life nearly ended. The first was 440 million years ago. A massive ice age wiped out 85% of all species on the planet. The second came around 375 million years ago, triggered largely by volcanic activity and ocean changes. The third, the deadliest of all, happened 250 million years ago and erased 96% of all species on Earth. It nearly ended complex life entirely. The fourth followed about 200 million years ago. And the fifth, the most famous, took out the non-bird dinosaurs 66 million years ago when an asteroid hit. Each of those events had a cause outside of biology itself. Ice, volcanoes, asteroids, ocean chemistry shifts driven by geology. The forces behind them were planetary or cosmic in scale. The sixth mass extinction is different. The cause is one species. Biologists now confirm that species are disappearing at a rate somewhere between 100 and 1,000 times faster than the natural background rate, the pace at which extinctions normally happen without major disruption. The primary drivers are habitat destruction, pollution, overhunting, invasive species introduced by human activity, and climate change layered on top of all of those. Unlike the asteroid strike that ended the dinosaurs, this extinction doesn't come with a visible impact. There's no crater. There's no smoke blocking the sky. It happens quietly. A forest gets cleared. A coral reef bleaches and dies. A wetland drains for a parking lot. Each event looks local and manageable, but at the global scale, the losses compound. And unlike the previous 5 extinctions, this one is accelerating. Researchers estimate that the current rate of species loss is speeding up, driven by the combination of direct habitat destruction and climate change simultaneously squeezing the ranges where species can survive. Here's why this should concern you even if you feel disconnected from wildlife. Biodiversity is the structural strength of ecosystems. The more species an ecosystem contains, the more resilient it is to disruption. A forest with 50 types of trees handles drought, disease, and pest outbreaks better than a forest with 5. An ocean with hundreds of fish species handles temperature shifts better than one dominated by a handful. Diversity is the safety net. Remove enough species and the net develops holes. Remove enough and the net tears. Food webs are interconnected. When species at one level collapse, it destabilizes everything above and below them. Prey animals multiply without predators. Plants go uncontrolled without grazers. Insects that pollinate crops disappear and take entire harvests with them. Scientists point to a critical threshold similar to the land transformation danger zone. Once enough keystone species, the ones that entire ecosystems depend on, are gone, the collapse of those systems can become self-reinforcing. The 6th extinction is moving too slowly to feel like an emergency in daily life. But in geological time, it's a flash. Future scientists, or whatever species inherits a planet humans left behind, would look at this period in the fossil record the way we look at the asteroid impact layer that ended the dinosaurs. The most alarming signal isn't the large, charismatic animals going extinct. It's what's happening to the smallest, least visible creatures. And one group in particular is sending a warning that cuts straight to the foundation of how food gets made. Nobody makes a documentary about insects going extinct. There are no campaigns to save the hoverfly, no viral videos of the last ground beetle, no charity merchandise for the common mayfly. Insects are too small, too numerous, and too easy to ignore. That invisibility is part of what makes their decline so dangerous. Over the past several decades, insect populations across many parts of the world have collapsed at a rate that researchers describe as dramatic. One landmark study conducted in German nature reserves found that total flying insect biomass had dropped by over 70% in less than 30 years. 70%. The researchers weren't measuring species counts. They were measuring total mass. Nearly 3/4 of all the flying insect matter in those protected areas was simply gone. Other studies across different continents have found similar patterns. Insect populations dropping dramatically in regions with no obvious single cause, no pesticide application nearby, no recent habitat destruction. Just a slow, sustained collapse that seems to track with rising temperatures, changing rainfall patterns, and the general disruption of the climate systems insects evolved to live inside. Here's why this matters at the scale of human survival. Insects pollinate roughly 75% of the flowering plant species that humans grow for food. Almonds, apples, blueberries, avocados, cucumbers. Most vegetables and fruits depend on insects, primarily bees, to reproduce. No pollination means no seeds. No seeds means no crop. A world without adequate insect pollinators is a world with drastically reduced food variety and yield. Insects also form the base of food chains that feed birds, fish, amphibians, and small mammals. When insect populations crash, the animals that eat them crash too. And the animals that eat those animals begin to starve. The collapse cascades upward through the food web in a pattern scientists call a trophic cascade. There's also the soil story tied to insects. Beetles, ants, termites, and earthworms physically break down dead organic matter and mix it into soil, creating the rich, aerated structure that plants need to grow. Without this biological processing, soils compact, lose fertility, and become harder for roots to penetrate. Agricultural yields drop even without a change in rainfall or temperature. What makes the insect situation especially hard to reverse is the timeline. Insect populations can recover if conditions improve, but climate change, habitat loss, and chemical use are all continuing simultaneously. The pressure isn't easing, it's compounding. Scientists who study insect populations use the phrase insect apocalypse carefully. They know it sounds alarming. They use it because the data gives them few gentler options. and the ocean is showing a parallel story. A system that covers over 70% of Earth's surface and produces roughly half the planet's oxygen is showing signs of stress in places so deep and so remote that the signals are only now becoming visible. Something is coming for the coral reefs, and the most shocking part is how far down it's already reached. Coral reefs cover less than 1% of the ocean floor, but they shelter roughly 25% of all known marine species. That ratio, tiny footprint, massive impact, is what makes their collapse so catastrophic. Most people know coral reefs as colourful, shallow water ecosystems. The Great Barrier Reef, the coral gardens of the Caribbean, places you see in nature documentaries, bright and dense with life. And yes, those shallow reefs are struggling badly. But the story that shook marine scientists in recent years goes deeper. Deep water corals, living at depths between 150 and 1,000 feet, were long thought to be insulated from surface warming. The water down there is cold, dark, and slow-moving. Changes on the surface were supposed to take decades to penetrate that far down. Scientists expected deep reefs to be refugees, places where coral could survive even as the surface warmed. In the past few years, researchers discovered mass bleaching events in deep water coral systems that had never been documented before. Deep bleaching, in water where temperatures were previously stable for centuries. The ocean heat had reached further than the models predicted, and it arrived faster. To understand why bleaching kills coral, you have to understand what coral actually is. A coral reef is a living structure built by tiny animals called coral polyps. These polyps live in a partnership with microscopic algae called zooxanthellae, which live inside the coral's tissues and provide up to 90% of its energy through photosynthesis. In return, the polyp gives the algae shelter and nutrients. When water temperatures rise even slightly, that partnership breaks. The coral expels the algae. Without its main energy source, the coral turns white, which is the bleaching. It's still alive, but barely. If the temperature stress continues for more than a few weeks, the coral starves to death. Once coral dies, the structure remains, but the ecosystem collapses. The fish that depended on it for shelter, the invertebrates that lived within it, the predators that fed on those creatures, all of them lose their habitat simultaneously. A reef that took thousands of years to build can functionally die in a single warm season. In the most severe bleaching event ever recorded, which began in 2023 and extended into 2024, scientists confirmed that bleaching had affected coral systems across all major ocean basins simultaneously. Every major reef region on the planet was hit in the same event. For the first time in recorded history, the bleaching was truly global. Some reefs have bleached multiple times now. Coral can recover from a single bleaching event if given enough time, roughly 10 years of stable, cooler conditions. But when bleaching happens back to back, the coral never gets that window. Recovery requires stability, and the ocean is no longer offering that. The Great Barrier Reef experienced its most severe bleaching on record in 2022, followed by another major event in 2024. 2 back-to-back strikes. Scientists are now mapping which sections have any realistic chance of recovery and which have crossed into permanent decline. Coral reefs are the visible edge of a much larger ocean crisis. But the most fundamental threat to the ocean, the one that makes everything else harder to survive, is something you can't see at all. And it's happening right now, in every ocean, on every reef, and across every square mile of open sea. 12,000 years ago, a period of warming ended the last ice age. Glaciers that had covered much of North America and Northern Europe began retreating. Over thousands of years, they pulled back, filling rivers, carving valleys, and raising sea levels as they went. It was one of the most dramatic climate transitions Earth ever experienced. Glaciers today are melting faster than they did during that transition. Let that land for a moment. The retreat happening right now, measured by satellite and on-the-ground sensors, is outpacing the melt rate of an event that fundamentally reshaped the planet. The world's glaciers, spread across mountain ranges on every continent except Australia, hold a massive amount of fresh water. The Himalayas alone, often called the Third Pole, feed rivers that provide fresh water to nearly 2 billion people. The Andes supply fresh water to dozens of cities across South America. Glaciers in Alaska, the Alps, and Central Asia feed rivers that communities depend on for drinking water, irrigation, and power generation. As those glaciers shrink, they go through two distinct phases. In the first phase, they release more water than usual, because the melt rate exceeds the rate of new snowfall. Rivers run higher. Seasonal flooding increases. This phase can last decades. It looks like abundance, but it's a withdrawal from a savings account that isn't being refilled. In the second phase, the glacier has thinned so much that summer melt drops sharply. The river it fed starts to shrink. Dry seasons get drier. Irrigation systems built over generations begin to fail. Cities and farmland that depended on predictable seasonal flows face shortages they have no infrastructure to solve. Multiple mountain glacier systems around the world are already entering that second phase. In places like Bolivia and Peru, smaller glaciers that once fed cities year-round are nearly gone. Communities that relied on them for generations are facing real water crises, not projected ones, right now. In northern India and Pakistan, where the Himalayan glaciers feed rivers used by hundreds of millions of people, scientists are watching the long-term trend with serious concern. The speed of the current melt also tells a story. Researchers analyzing ice core records and comparing them to satellite data confirmed that the current rate of global glacier mass loss has no equivalent in the past 12,000 years. The pace at which glaciers are shedding ice today is outside the range of natural variability documented across that entire window. One striking comparison: the Rhone Glacier in the Swiss Alps, famous enough to be a tourist destination for over a century, has retreated nearly 2 miles since 1870. In the last 20 years alone, it retreated more than in the preceding 120. The acceleration is visible within a single human lifetime. Globally, scientists estimate that if current warming trends continue, a large percentage of mountain glaciers outside the poles will be significantly reduced by the end of the century. Some of the smallest and most critical, the ones feeding river systems with no other major source, will be gone. The glaciers are a water story, a sea level story, and a food story all in one. And just as they are accelerating their decline, the world's largest industrial systems are accelerating in the opposite direction, pushing out more fuel than at any point in history. Every year, scientists who track global energy use compile their data. They measure how much oil was pumped, how much coal was burned, how much natural gas was consumed. They've been doing this for decades, watching the trend line through the rise of renewables, through major climate agreements, through every promise made at every international summit. In 2024, the world burned more fossil fuel than in any year in history. Every previous record broken. This happened the same year that global average temperatures also hit an all-time high. The same year that ocean temperatures broke records. The same year that scientists confirmed 18 of 31 planetary vital signs had reached their worst readings ever. All of it happening simultaneously, while fossil fuel consumption set a new ceiling. To picture the scale of fossil fuel consumption in a single year, consider this. The amount of energy released by burning all the oil, gas, and coal used globally in 1 year is roughly equivalent to detonating a nuclear weapon every few seconds, continuously for the entire year, every moment, around the clock, for 365 days. That energy moved cars, flew planes, heated homes, ran factories, powered servers. It also released more greenhouse gases into the atmosphere than any prior year, adding to a cumulative total that has been building since the industrial age began. The existence of renewable energy made this record stranger to explain. Solar and wind power both grew at record rates in 2024. More renewable capacity was added globally than in any previous year. And yet total fossil fuel use went up anyway, because global energy demand grew faster than renewables could fill. The world added clean energy and still burned more coal and oil than ever before. Scientists watching this data use the word alarm directly. The trajectory of emissions directly determines how close the planet gets to the tipping point thresholds identified in climate research. Every year of record emissions shortens the remaining time before those thresholds become unavoidable. What makes 2024 particularly significant is its position in the timeline. The major international climate agreements, including the targets set at the Paris Agreement in 2015, were built around the goal of limiting warming to well under 2 degrees Celsius, above pre-industrial levels. Scientists estimated that to stay within that window, global emissions needed to peak and begin declining sharply by the early 2020s. 2024 set an all-time emissions record. The gap between the targets agreed to in international negotiations and the actual behavior of the global economy has never been wider. Scientists call this the emissions gap, and in 2024, it grew. The story of 2024 emissions sits inside a larger context. The world is simultaneously facing unprecedented glacial loss, coral bleaching, insect collapse, permafrost thaw, and Amazon degradation, all while pumping more greenhouse gases into the air than ever before. Each of these crises feeds the others. But some of the consequences of those gases don't wait for the long term. Some of them arrive fast, violently, in the form of heat so extreme that the human body simply cannot survive it. The human body has limits. Under normal conditions, the body cools itself through sweating. Sweat evaporates from the skin, carrying heat away with it. As long as the air is dry enough and cool enough to accept that evaporation, the body manages. Athletes run in summer heat. People work outdoors in tropical climates. The body adapts within a range. But there's a boundary beyond which sweating stops working. Scientists measure it using something called wet bulb temperature. This combines actual air temperature with humidity to calculate how effectively evaporation can cool the skin. At a wet bulb temperature of 35 degrees Celsius, which is 95 degrees Fahrenheit under full saturation humidity, evaporation from the skin essentially stops. The body can no longer shed heat. Even a healthy, resting person in the shade would see their core temperature rise uncontrollably. Survival time at that threshold is a matter of hours. Before 2024, wet bulb 35 had been recorded only in isolated locations, and very briefly. Researchers had described it as a theoretical danger zone that climate change might eventually make more common. Then came back-to-back heat events in South Asia and the Persian Gulf that pushed readings close to and at that threshold for extended periods. These events killed people. The full toll is still being studied because heat deaths are often miscounted, recorded as cardiac events, organ failure, or other heat-related complications, rather than directly attributed to temperature. But here's the longer concern. Current climate projections show that if warming continues on its present trajectory, wet bulb 35 conditions will become regular summer occurrences across large portions of South Asia, the Middle East, and sub-Saharan Africa by mid-century. Regions where hundreds of millions of people live, many of them working outdoors in agriculture with no access to air conditioning. For those populations, this isn't a future risk. It's a trajectory that arrives within the lifetimes of people alive today. Extreme heat also compounds other crises. Crops stressed by heat produce less. Livestock stressed by heat grow slower and become more vulnerable to disease. Rivers fed by snowpack shrink as winter snowfall decreases. Power grids built for a cooler climate buckle under the demand of widespread air conditioning use during extreme heat events. Cities face their own version of this problem. Urban areas absorb and retain heat more than rural land because of concrete, asphalt, and reduced vegetation. This creates what scientists call the urban heat island effect. During a heat wave that drives rural temperatures to dangerous levels, city temperatures can run several degrees higher still. And here's the detail that public health researchers keep raising. Heat stress accumulates. A person who survives several extreme heat days in a row, each one below the lethal threshold, builds physiological stress that makes the next heat event more dangerous. The body doesn't fully recover between events if events cluster closely together, which is exactly what climate projections show happening more frequently. The human body was built for a range of temperatures that Earth no longer reliably provides in all the places where people have built their lives. But the heat on land tells only part of the story. Underneath the ocean, something is happening that takes heat absorbed at the surface and ensures it doesn't leave the climate system for centuries. A feedback loop that works entirely out of sight and has no off switch. Most people, when they think about climate change, picture a one-way street. Humans burn fuel. Carbon dioxide goes up. Temperatures rise. The problem is the emissions. Stop the emissions and the rise stops. That picture is partially true, but it leaves out something that climate scientists spend a significant amount of time worrying about. Feedback loops. Specifically, the ones that don't wait for humans to make them worse. A feedback loop in climate science is a process where warming causes a change, and that change causes more warming, which causes more of the change. The loop closes on itself. It amplifies the original signal without any new input required. The one hiding beneath the ocean is particularly consequential. Here's how it works. The ocean absorbs roughly 90% of the excess heat trapped by greenhouse gases. It also absorbs large amounts of carbon dioxide directly from the atmosphere. This absorption has been a buffer, slowing the rate of warming that the atmosphere would otherwise experience. The ocean has been doing humanity a favor without being asked. But that absorption comes with a cost. When the ocean absorbs carbon dioxide, it reacts with seawater to form carbonic acid. This makes the ocean more acidic. A more acidic ocean is harder for shell-forming creatures, including many types of plankton, to survive in. And here's where the loop begins. Certain species of plankton, particularly a type called coccolithophores, form calcium carbonate shells as they grow. When they die, their shells sink to the ocean floor, carrying the carbon they absorbed with them. This process, called the biological pump, has been removing carbon from the surface ocean and burying it deep for hundreds of millions of years. As acidification increases, the shells of these plankton thin and weaken. Some research suggests the biological pump is already becoming less efficient. As it slows, more carbon stays in the surface ocean. More carbon in the surface ocean means more gets exchanged back into the atmosphere. More atmospheric carbon means more warming. More warming means more ocean heat and acidification. The loop tightens. There's a second loop operating simultaneously. Warm water holds less dissolved gas than cold water. As the ocean warms, its capacity to absorb carbon dioxide physically decreases. So, as the planet warms, the ocean becomes progressively less able to do the buffering job it's been doing. The warming accelerates. Neither of these loops is flipping a switch overnight. They operate on long timescales, but they're both moving in the wrong direction right now, and their effects will become increasingly significant as temperatures continue rising. The key phrase scientists use is reduced carbon sink efficiency. The ocean is still absorbing carbon, but it's absorbing a smaller percentage of what humans emit each year than it did decades ago. The buffer is weakening. What makes this feedback loop different from some others is that it's already measurable. Scientists have documented increasing ocean acidity across every major ocean basin. They've tracked the weakening of shell formation in marine organisms. The data exists. The trend is clear. And the compounding effect is this. Every feedback loop that activates makes every other feedback loop easier to activate. The system that keeps Earth stable is becoming progressively less stable. While the ocean changes silently, something closer to human experience is also shifting. The systems that produce the food billions of people eat every day are starting to show serious signs of strain. The connection between a warming planet and an empty plate is shorter than most people realize. Food comes from soil, water, sunlight, and pollinators. Change any one of those significantly, and the system strains. Change all four simultaneously, and you're describing the world that climate change is building right now. Start with soil. Healthy agricultural soil is a living system. It contains billions of microorganisms per teaspoon, bacteria, fungi, and tiny creatures that break down organic material, cycle nutrients, and maintain the structure that plant roots need to penetrate and absorb water. This biology took centuries to develop and depends on stable temperature and moisture conditions. Extended heat drives moisture from topsoil faster than crops can absorb it. Drought hardens the surface and reduces the soil's ability to absorb rainfall when it does come, leading to runoff rather than absorption. Repeated drought and heat cycles kill off the microorganism communities that maintain soil fertility. Agricultural land that loses this biological activity becomes harder and less productive over time, even when rainfall returns. Then there's water. Agriculture uses roughly 70% of all fresh water consumed by humans globally. That water comes from rivers, groundwater aquifers, and the seasonal snowpack that feeds river systems from melting glaciers and mountain snow. All three of those sources are under stress simultaneously. Rivers fed by glaciers are entering the phase described earlier, where the initial surge from faster melting eventually gives way to reduced summer flow as the glaciers thin. Aquifers, the underground reservoirs drilled by millions of wells worldwide, are being drawn down faster than they recharge. The Ogallala Aquifer, which provides water to about a third of all groundwater used for agricultural irrigation in the United States, is being depleted at rates that could render large portions of it unusable within decades. Add to this the pollinator story. The collapse of insect populations discussed earlier feeds directly into crop yield. Crops that depend on pollination, and that includes most fruits, many vegetables, and several nuts that form critical parts of human diets globally, face potential yield reductions that would require massive agricultural restructuring to compensate for. Extreme weather compounds everything. Floods destroy crops by drowning root systems, spreading disease, and physically washing away topsoil. Droughts kill crops through moisture stress. Abnormally late or early frosts, which are becoming more common as climate instability disrupts seasonal patterns, can kill blossoms before they're pollinated or freeze mature crops before harvest. Here's a number with weight behind it. A study modeling food security under various climate scenarios found that global crop yields for staple crops, including wheat, rice, and maize, could decline by double-digit percentages by mid-century under medium warming scenarios. The same scenarios project that the regions most heavily hit would be the ones where food insecurity is already highest. The food system also has very little slack. Modern agriculture is built on efficiency, just-in-time supply chains, and tight margins. A bad harvest in one major producing region sends prices up globally within weeks. A bad harvest in multiple regions simultaneously creates food shocks that cascade through economies and governments. And here's what ties this directly to the coastlines. The cities and farmland that feed the most people often sit at low elevation. Sea level rise doesn't wait for food systems to stabilize before it arrives. Every major coastal city on Earth was built with an assumption baked into its foundation, that the sea would stay roughly where it was. Cities took centuries to develop. The engineers who built New York's subway didn't think about sea level rise. The architects who raised London's buildings near the Thames didn't calculate a warmer ocean. The planners who expanded Miami's grid across low-lying land didn't account for the eventual disappearance of that land's buffer from the sea. The sea was a constant, a given, part of the background. That assumption is now wrong. Sea levels have already risen by roughly 8 inches since 1900. Most of that rise happened in the second half of the 20th century, and the rate is accelerating. The current rate of rise is roughly 4 times faster than the average rate during the 20th century. The sources of rising sea are two distinct mechanisms. The first is thermal expansion. Water physically expands when it warms. As the ocean absorbs heat, its volume increases. This effect alone would raise sea levels meaningfully over the coming century, even if no ice melted at all. The second source is ice melt. Glaciers, the Greenland ice sheet, and the Antarctic ice sheets are all losing mass and sending that water into the ocean. The combined contribution of these ice losses is the larger and faster growing share of current sea level rise. Scientists use models to project future rise, and the range of those projections is wide because it depends heavily on what the ice sheets do. If they melt slowly and linearly, projections for the end of this century are roughly 1 to 2 feet of additional rise. If ice sheet dynamics accelerate, including the collapse of major glacial systems in West Antarctica, projections move significantly higher, with some models reaching 4 to 6 feet or more by 2100. Even the conservative end of that range creates serious problems. Miami sits at an average elevation of roughly 6 feet above current sea level. During high tides combined with storm surges, parts of Miami already flood. With 2 feet of additional rise, the frequency of those flood events multiplies dramatically. With 3 or 4 feet, large portions of the city face regular inundation. The city's drainage system, built to push water into the sea, struggles to function when the sea is higher than the land it's supposed to drain into. Miami is the most visible case in the United States, but it's far from alone. Bangladesh has roughly half of its land within a few feet of sea level, and supports a population of nearly 170 million people. The Netherlands has built an extraordinary system of dikes and water management to keep low-lying land habitable, but even that engineering marvel has limits. Jakarta, Indonesia's capital, has been sinking partly from groundwater extraction and faces some of the most severe flooding risk of any major city on Earth. And here's the detail that makes the math so difficult. Sea level rise doesn't arrive as a slow, steady creep that gives people time to move. It arrives through storms. A sea level 1 foot higher than baseline turns a 25-year storm event into a 10-year event. 2 feet turns it into a 5-year event. The flooding becomes frequent enough to be functionally permanent in the lowest lying areas. Insurance markets are already responding. Several major insurance companies have begun withdrawing from coastal markets in Florida. Property values in some low-lying areas are beginning to reflect risk that wasn't previously priced in. Economists call this a climate discount. Scientists call it the beginning of a very long, very expensive forced migration. The sea level story is tightly linked to the ice sheet story, and the ice sheet most capable of delivering a sudden, dramatic contribution to sea level rise sits at the bottom of the world, held in place by a geographic feature that is itself becoming unstable. Here is the uncomfortable truth that climate scientists carry with them. Even if every country on Earth stopped burning fossil fuels tomorrow, certain processes already in motion would continue for decades, some for centuries. The climate system has a delay built into its physics, and that delay means the consequences of past emissions haven't fully arrived yet. Scientists call this committed warming. The carbon dioxide already in the atmosphere will continue trapping heat for a long time, because carbon dioxide doesn't disappear quickly. A molecule of carbon dioxide released today stays in the atmosphere for anywhere between 20 and 200 years, with some fraction persisting for thousands of years. The warming that molecule causes doesn't happen all at once. It accumulates gradually as the ocean slowly absorbs heat and the atmosphere adjusts. Think of it like turning on an oven and then immediately switching it off. The inside keeps getting hotter for a while after the heat source stops. Earth's climate works the same way. The heat already committed from past emissions hasn't fully expressed itself yet. Current estimates suggest that even if emissions stop today, the planet would still warm by roughly an additional 0.5 to 1 degree Fahrenheit from emissions already in the atmosphere. That extra push is locked in. It's already paid for. What that means in practical terms is that certain consequences are no longer avoidable. More extreme heat waves, more intense hurricanes, more frequent flooding in coastal areas, greater stress on coral reefs, continued glacier retreat. These outcomes aren't predictions of what might happen if things go wrong. They're descriptions of what's coming regardless of what happens next. Because the cause already occurred. This doesn't mean future emissions don't matter. They matter enormously. The difference between an additional ½ degree and an additional 3 degrees is the difference between a difficult future and a catastrophic one. Every fraction of a degree avoided by cutting emissions reduces the severity of what's coming. The math of mitigation still works. It just no longer works as prevention in every sense. For certain systems, it works as damage reduction. Scientists are careful to explain this distinction because it affects how people think about action. The argument, "It's already too late, so why bother," is scientifically wrong. The argument, "Some things are already locked in and we need to both reduce emissions and adapt to what's coming," is accurate. The adaptation part of that is where many governments are significantly underprepared. Most infrastructure planning still uses historical climate data as its baseline. Bridges are built to handle the flood levels recorded over the past 100 years. Drainage systems are sized for the rainfall patterns of the 20th century. Power grids are designed for the temperature ranges of previous decades. All of that historical data now describes a climate that no longer exists. The committed warming story also intersects directly with the tipping point debate. If certain tipping points are triggered by levels of warming already locked in, then even zero future emissions wouldn't prevent those triggers from being reached. The Greenland ice sheet, the Amazon, and boreal permafrost are all responding to current temperatures. Current temperatures already include committed future warming that hasn't fully arrived yet. Some scientists argue that this means the conversation needs to expand urgently beyond cutting emissions to include direct intervention in the climate system, using technology to pull carbon from the atmosphere, or to reflect some sunlight back into space. Others argue those approaches carry their own risks and unknowns that make them dangerous to rely on. That debate is happening right now at the highest levels of climate science. And at the center of it is a question nobody has been able to answer with certainty. Exactly when does the Amazon cross the line it cannot come back from? The Amazon holds more biodiversity than any other ecosystem on Earth. It produces roughly 20% of the planet's oxygen through the combined photosynthesis of hundreds of billions of trees. Its moisture cycle influences rainfall patterns across the entire South American continent, and through atmospheric connections, weather systems far beyond it. Scientists have known for decades that this system has a vulnerability, a threshold, a point beyond which the feedback loops, maintaining the forest flip direction and begin destroying it instead of sustaining it. The question keeping researchers awake is how close that threshold actually is. The most widely cited estimates put the danger zone somewhere between 20 and 25% total deforestation of the original Amazon basin. Clearing beyond that amount could collapse the internal moisture cycle enough to push even untouched regions of the forest into a permanent dry state. Once the tree cover falls below a critical density, the forest can no longer generate enough of its own rainfall to sustain itself. It transitions into a savanna-like state, releasing centuries of stored carbon in the process. Current deforestation sits at roughly 20% of the original Amazon, with significant regional variation. Parts of the southern and eastern Amazon are already past that regional threshold by some measurements. But deforestation isn't the only pressure. Climate change is simultaneously reducing rainfall and extending dry seasons across the basin. When scientists layer the deforestation data and the climate data together, the combined stress pushes the effective tipping point threshold lower than the original estimates suggested. A research paper published in the journal Nature in recent years found that more than 75% of the Amazon basin was showing signs of reduced resilience, losing its ability to bounce back from disturbances like drought and fire, trees dying faster than before, recovery after dry seasons slower than historical norms, the biological signals of a system under accumulating stress. The disagreement among scientists isn't about whether the threshold exists. The physics of the moisture cycle makes the threshold real. The disagreement is about timing. Some researchers believe the tipping point could arrive within decades under current trajectories. Others place it further out, contingent on deforestation rates slowing significantly. Still others argue that the definition of tipping point needs to be rethought, because the Amazon may be transitioning gradually rather than flipping suddenly. What nobody disputes is this. The forest that was supposed to be one of humanity's largest natural allies against climate change is shrinking, drying, and losing resilience simultaneously. And the carbon it holds, enough to meaningfully accelerate global warming if released, is no longer as locked away as it once was. There's a detail that makes this particularly urgent at the policy level. The Amazon tipping point, once crossed, is effectively permanent on human timescales. A savanna replacing a rainforest doesn't recover back to a rainforest in decades. It might not recover in centuries, even with active replanting efforts, because the moisture cycle that made the rainforest possible no longer exists. Scientists watching this situation have increasingly stopped talking about the Amazon tipping point as a future risk and started describing it as a present emergency that requires immediate intervention. And right above the Amazon story, in terms of technological capacity to see what's happening, are the supercomputer models now running simulations sophisticated enough to project Earth's climate behavior decades ahead. What those models are showing in their latest runs is the next piece of the picture. Climate models have existed since the 1960s. The early versions were simple, rough approximations of how the atmosphere absorbs heat. They ran on machines that would seem laughably underpowered by today's standards, and produced projections with enormous uncertainty ranges. The models running today are a different category of tool entirely. Modern climate supercomputers simulate the atmosphere, the ocean, the land surface, sea ice, and the carbon cycle all simultaneously. They divide Earth's surface into a grid of cells, each covering a few miles, and calculate how heat, moisture, wind, and chemistry interact at every point on that grid, at every hour, across decades of simulated time. Some of the largest models track hundreds of variables simultaneously. Running a single century-long climate simulation on these systems takes weeks of continuous computing. The sheer complexity of these models is what makes their agreement so significant. Different research centers, in different countries using different programming approaches, consistently produce models that agree on the major trends. Warming is accelerating. Extreme events are becoming more frequent. Sea levels are rising. The Arctic is warming faster than the global average. Ice is shrinking. What the latest generation of models is showing goes beyond confirming known trends. It's revealing dynamics that earlier models were too coarse to detect. One major finding from recent high-resolution model runs is the behavior of the jet stream, the powerful band of winds in the upper atmosphere that drives weather patterns across North America and Europe. As the Arctic warms faster than the tropics, the temperature difference that powers the jet stream weakens. A weaker jet stream meanders more. It develops large, slow-moving loops. And a slow-moving loop means a weather system, whether it's a heat dome, a flood event, or a cold snap, sits in place for much longer than it historically would have. This mechanism explains why certain extreme weather events in recent years lasted so much longer than historical records suggested was normal. Heat waves that lasted weeks, flooding that persisted for days longer than comparable historical storms. A weakened jet stream is a direct prediction of the climate models, and it's showing up in real-world weather exactly as predicted. Another pattern emerging in the latest model runs is what researchers call precipitation whiplash. As the climate warms, the atmosphere holds more moisture, but it distributes that moisture more unevenly. Dry regions get drier, wet events get wetter. And regions swing between extremes more rapidly, going from drought to flood and back, without the stable transition periods that ecosystems and agricultural systems depend on. California has experienced this directly. Extended droughts followed by atmospheric river events delivering extreme rainfall. The soil, hardened from drought, can't absorb the sudden water. It runs off. Flash floods occur. Then drought resumes. The models are also flagging risks that haven't fully materialized yet but appear in projections across multiple research centers. One of the most discussed is the potential weakening of the Atlantic overturning circulation, the massive ocean current system that carries warm water north and drives much of Western Europe's mild climate. Some models suggest this circulation has been slowing. Others debate the magnitude and speed. But its potential weakening, and what that would mean for temperatures across the North Atlantic, is something climate scientists are watching closely, and the supercomputers are tracking in every major simulation. The models don't lie, they simplify. And their simplifications have consistently proven to underestimate the speed of change in the real world. What scientists have been adding to the models to close that gap is more data from the poles. And the data coming from the bottom of the world, from the ice sitting over West Antarctica, is the part of the picture that changes the sea level story entirely. In science, words like death spiral don't appear in peer-reviewed research easily. Scientists choose language carefully. They hedge, they qualify. They write suggests instead of proves, and may contribute to instead of causes. That's how science works. Precision over drama. So when a secondary emergency paper, signed by over 14,000 scientists and published in a major scientific journal, used the phrase death spiral to describe Earth's current trajectory, researchers across the field paid attention. This paper came after the 2017 warning letter. It was a response to the lack of action in the years that followed. The scientists who signed it weren't trying to make headlines. They were doing something unusual for their profession. They were expressing, in the clearest language they could, that the situation had moved past the point of ordinary scientific caution. The paper laid out a specific argument. Earth's climate systems are interconnected in ways that create compounding risks. Each system that degrades makes the next one more vulnerable. The loss of Arctic sea ice speeds up permafrost thaw. Permafrost thaw releases methane that warms the atmosphere further. More atmospheric warming dries out the Amazon. A drying Amazon releases stored carbon. That carbon accelerates ocean warming. Ocean warming bleaches coral and weakens the biological pump. A weaker biological pump leaves more carbon in the atmosphere. Each step in that chain had already been documented individually in peer-reviewed research. What the death spiral paper argued was that viewing these events separately, as different issues managed by different scientific disciplines and different policy departments, was itself the critical mistake. The systems don't operate separately. They operate as a web, and the web was tightening. The phrase death spiral referred specifically to this compounding dynamic. A spiral, in the scientific sense, is a process that feeds itself and accelerates over time. Each rotation moves faster than the last. The concern was that Earth's interconnected climate systems were beginning to enter a state where each degradation triggered further degradation, and the spiral was picking up speed. Over 14,000 scientists co-signed the document. Researchers from biology, oceanography, atmospheric science, glaciology, ecology, and dozens of other disciplines. The breadth of expertise behind the signatures was deliberate. The message was that this wasn't one discipline sounding an alarm about its own corner of the data. Every corner of the data was sending the same signal. Public response to the paper was mixed. Some media outlets covered it prominently. Others gave it limited space. Some commentators argued the language was too alarming to be taken seriously. Scientists responding to those critiques pointed back to the data behind each compounding step and asked what language would be more appropriate. The paper identified specific interventions that could interrupt the spiral: rapid emissions reduction, protection and restoration of major carbon sinks, particularly forests and wetlands, changes to land use practices, investment in clean energy at a scale that would genuinely replace fossil fuels rather than supplement them. The authors were explicit that these interventions were still possible. The spiral was not yet irreversible, but the window in which intervention could work was closing. And the systems most capable of driving the spiral forward, if they crossed their own tipping points, would remove that window entirely. One of those systems holds a specific geographic vulnerability that no other ice system on Earth shares, a structural weakness built into the very bedrock it sits on, and scientists have given that vulnerability a name: the marine ice sheet instability. What it means for the future is something that changes the sea level projections in a fundamental way. The West Antarctic ice sheet sits over bedrock that slopes downward away from the coast. Picture a bowl where the sides are at the ocean and the center is the lowest point. That shape matters enormously. As warm ocean water eats at the edges of this ice sheet from below, the ice retreats inland. But as it retreats, it moves onto deeper bedrock, where more of the ice base is in contact with the warm water. More contact means faster melting. Faster melting means the ice retreats further inland, onto even deeper ground. The deeper the bedrock, the more ice is exposed to ocean water, the faster the retreat. This self-reinforcing retreat has a scientific name: marine ice sheet instability. And unlike many climate risks that depend on future decisions, this instability may already be underway in parts of West Antarctica. The Thwaites Glacier is the specific system scientists are watching most closely. It's roughly the size of Florida. Scientists have nicknamed it the Doomsday Glacier, though they use that term cautiously, because its collapse wouldn't be instant and wouldn't cause doom on its own. But its potential contribution to sea level rise is enormous, and its behavior controls the stability of much of the surrounding ice sheet. Researchers have documented warm ocean water intrusion beneath the Thwaites Glacier, melting it from below. Satellite data shows the glacier's grounding line, the point where the ice transitions from resting on bedrock to floating on the ocean, retreating inland. And the bedrock behind that grounding line slopes downward, exactly the configuration that makes marine ice sheet instability self-reinforcing. If Thwaites were to fully collapse, its own contribution to global sea level rise would be roughly 2 feet. Significant but manageable with major adaptation efforts. The more serious concern is what Thwaites holds back. Behind the Thwaites, glacier sits a larger portion of the West Antarctic ice sheet. Thwaites acts as a plug. If it destabilizes significantly, the ice behind it could begin flowing toward the ocean much faster. The full collapse of the West Antarctic ice sheet, which scientists consider a long-term risk rather than an imminent one, could raise global sea levels by roughly 11 feet. 11 feet would permanently inundate enormous areas of coastline globally. Cities across every continent would face losses that make current climate projections look modest. The timeline for Thwaites is genuinely uncertain. Some models project significant deterioration within decades. Others suggest longer timescales. What researchers agree on is that the process already appears to be underway, and the geometry of the bedrock makes reversal extremely difficult, even if ocean temperatures were to cool. Scientists deployed the first autonomous underwater vehicle beneath Thwaites in recent years, mapping the seafloor and measuring the temperature and movement of water beneath the glacier. The data they brought back showed warm water reaching further beneath the glacier than previous measurements had indicated, melting the base in patterns that suggest the process is more advanced than earlier models projected. The Thwaites story is uncomfortable precisely because it sits at the intersection of a known physical mechanism, a documented current process, and a timeline that remains genuinely uncertain. The physics says the collapse will continue. The data says it's already happening. The unknowns are speed and scale. And while Thwaites captures the sea level story, the most immediate and dramatic accelerant of warming sits underground across the northern latitudes, releasing something far more potent than carbon dioxide. in quantities that no human decision can stop once the thawing crosses its own threshold. Carbon dioxide is the greenhouse gas most people know. It drives the bulk of human-caused warming. Governments track it. Companies report it. Climate agreements set targets around it. Methane is its lesser-known relative, and in some ways is far more dangerous over short timescales. Molecule for molecule, methane traps roughly 80 times more heat than carbon dioxide over a 20-year period. It breaks down faster in the atmosphere, which means its long-term warming effect is lower than carbon dioxide's. But in the near term, the decades that matter most for avoiding tipping points, a pulse of methane into the atmosphere has a warming impact that dwarfs the same mass of carbon dioxide. Permafrost holds methane. The bubbling Siberian lakes described earlier release it. The ocean floor holds additional methane in a frozen form called methane hydrates. Stable only under specific pressure and temperature conditions that warming waters are beginning to disturb. And the stomachs of billions of livestock, plus the decomposition of waste in landfills, release significant methane from human activity. Here's the piece that makes scientists most uneasy. The natural methane sources, the ones sitting inside permafrost and ocean sediments, are not controlled by human decisions. They respond to temperature. As temperatures rise, they release more methane. As they release more methane, temperatures rise faster. As temperatures rise faster, they release more methane again. This loop, if it accelerates significantly, could overpower the emissions reductions that human societies are capable of making. Scientists call this scenario a methane burst, or methane pulse. And while the full version of it remains uncertain, smaller versions of it are already happening. The methane concentration in Earth's atmosphere hit a record high in recent years, and a significant part of that rise came from natural wetland and permafrost sources, not just from agriculture or fossil fuels. The volume of methane potentially locked in Arctic permafrost alone is staggering. Scientists have estimated that the permafrost zone holds enough organic carbon to release greenhouse gases equivalent to multiple decades of current human emissions, if substantial portions of it thaw and decompose. Nobody is predicting a sudden catastrophic release. The thawing is gradual, but gradual, in this context, means happening over decades, not centuries, within the lifetimes of people alive today. And each additional degree of warming thaws more ground, exposing more organic material to decomposition, releasing more methane and carbon dioxide, warming the planet further. Researchers who study the Arctic describe a particular visual that captures the scale. Flying over Siberia and seeing new lakes appearing where there was once flat frozen ground. The land literally collapsing as the permafrost beneath it melts and the soil settles. Each new lake is a new methane source, and they're appearing faster every decade. The methane story, combined with the carbon dioxide story, the ice story, and the deforestation story, adds up to a picture where natural systems are beginning to compete with human activity as drivers of warming. And at some level of warming, those natural drivers may dominate entirely. While methane threatens to overwhelm the atmosphere, something else is being quietly drained from the planet's surface. Something that billions of people drink, bathe in, and grow food with. Something that rivers, lakes, and underground reserves have held for thousands of years, but are now losing in every region simultaneously. Water covers roughly 70% of Earth's surface. That number makes freshwater scarcity seem impossible, but only about 2.5% of all water on Earth is fresh. And of that fraction, the vast majority is locked in glaciers and ice sheets. The amount available in rivers, lakes, and accessible underground aquifers amounts to a tiny sliver of all the water on the planet. That tiny sliver is now shrinking on every continent at the same time. Glacier-fed rivers are the most visible part of this story. As described earlier, glaciers are entering their second phase, where the initial surge of meltwater begins to decrease as the glaciers thin. Rivers that entire civilizations built around are becoming less reliable. Seasonal flows that farmers counted on for thousands of years are shifting and weakening. But the underground story is equally serious and far less visible. Aquifers are underground layers of rock, sediment, or soil saturated with water. They form over thousands of years as rainfall percolates through the ground and accumulates. In many parts of the world, they represent the only significant water source for farming and drinking water, and they're being drawn down far faster than they recharge. The Central Valley of California, one of the most productive agricultural regions in the world, sits over aquifers that have been pumped so aggressively that the land above them is physically sinking. In some areas, the ground has dropped by more than 30 feet over the past century. Once the aquifer material compacts from over-extraction, its ability to hold water permanently decreases. That storage capacity doesn't come back. The same pattern of over-extraction and land subsidence is documented across large parts of India, Pakistan, China, Iran, Mexico, and the American Midwest. The world's breadbaskets are pulling water from underground reserves that accumulated over millennia and will not refill on any human timescale. Lakes are telling a parallel story. Satellite data tracking global lake water volumes found that more than half of the world's large lakes have shrunk significantly over the past few decades. The causes include increased evaporation from warming temperatures, reduced inflow from melting glaciers and reduced snowpack, and direct human extraction. The Aral Sea, once one of the largest lakes in the world, is now largely a dry basin. Lake Mead, the largest reservoir in the United States, reached historically low levels in recent years. The combination of glacier loss, aquifer depletion, and lake shrinkage is happening simultaneously. The systems aren't independent. They're all responding to the same drivers: rising temperatures, shifting precipitation patterns, and direct human overuse. Fresh water scarcity connects directly to food security, since agriculture consumes most of the fresh water humans use. It connects to public health, since inadequate clean water drives disease. It connects to economic stability, since regions that lose reliable water access face agricultural collapse and population displacement. Scientists studying global hydrology use the phrase water stress to describe regions where demand exceeds reliable supply. Currently, roughly a third of the world's population lives in water-stressed regions. Under mid-century warming projections, that proportion grows significantly. The water story is hidden in plain sight. Rivers look like rivers. Taps still run. The depletion happens underground and upstream, invisible until it isn't. And when fresh water disappears from an ecosystem, it doesn't just affect humans. The biodiversity that depends on rivers, wetlands, and lakes begins to fail, which leads back to a deeper structural question about how resilient the remaining ecosystems actually are. An ecosystem with many species is like a building with many support beams. Remove one beam and the structure adapts. The load shifts. The other beams compensate. Remove 5 beams and the building is still standing, but it's noticeably weaker. Remove enough beams and the building collapses. Not gradually, but suddenly, once the remaining structure can no longer distribute the load. Biodiversity works the same way. Each species in an ecosystem plays a role. Predators control prey populations. Prey animals prevent plants from being overgrazed. Plants hold soil, cycle nutrients, and produce oxygen. Decomposers break down dead material and return it to the soil. Pollinators enable plant reproduction. Seed dispersers spread plants across landscapes. When species disappear, the ecosystem reorganizes around what remains. It adapts. But each adaptation leaves the system slightly less capable of handling the next disruption. The redundancy decreases. The web of relationships thins. Scientists identify certain species as keystone species, ones whose role in the ecosystem is disproportionately large relative to their population size. Wolves in Yellowstone are a famous example. Remove the wolves and deer populations exploded. Deer overgrazed riverbanks. Riverbanks eroded. River courses changed. Fish habitats degraded. Birds that nested in riverside vegetation disappeared. One predator, removed from the system, cascaded its effects across dozens of other species and altered the physical landscape. That cascade is happening at a global scale right now, driven by the sixth mass extinction. The keystone species going extinct aren't just ecologically important. They're load-bearing beams in systems that feed people, clean water, and regulate local climates. Mangrove forests are one striking example. These coastal ecosystems sit at the boundary of land and sea, their roots tangled in salt water. They shelter juvenile fish populations, filter water, sequester carbon at rates higher than most tropical forests, and absorb storm surge energy that would otherwise hammer coastlines directly. A healthy mangrove forest can reduce the destructive power of a storm surge by as much as 50 to 70%. Mangroves are disappearing at rapid rates globally from coastal development, pollution, and rising sea temperatures. Every mile of mangrove lost removes a natural buffer that protected coastlines for thousands of years, and a nursery for fish populations that feed millions of people. Wetlands offer a parallel story. They filter agricultural runoff before it reaches rivers. They store carbon. They absorb excess rainfall and release it slowly, reducing flood peaks. Their drainage for agriculture eliminates all of those functions simultaneously. Here's what makes the biodiversity loss story different from the emission story. You can, in theory, stop burning fossil fuels, and the atmospheric concentrations of greenhouse gases will eventually stabilize and begin declining. Species extinction is permanent. Once a species is gone, the ecological role it played has to be compensated by something else, if anything can compensate at all. There's no equivalent of pulling carbon back out of the atmosphere. There's no recovery mechanism for extinction. The compounding of all these losses, water, biodiversity, soil, coral, forest, ice, is what gives the death spiral paper its weight. No single loss is necessarily civilization ending alone. Together, they reduce Earth's capacity to sustain the systems humans depend on, step by step, beam by beam. And while these losses accelerate in the present, something extraordinary is waiting in the deep future. A change so fundamental that it makes all current climate concerns look temporary in comparison. And it has nothing to do with what humans do or don't do. Earth's surface is always moving. Always. The ground beneath your feet right now is sliding at roughly the same speed your fingernails grow, a few inches per year. The 7 major tectonic plates that form Earth's outer shell have been drifting for billions of years, colliding to form mountain ranges, splitting apart to open oceans, and rearranging the map of the world over timescales that make human history look like a single breath. 250 million years ago, all of Earth's continents were merged into one massive landmass called Pangaea. It stretched from pole to pole, a single connected block of land surrounded by one global ocean. Then it began to break apart. Over tens of millions of years, the pieces we now call continents drifted to roughly where they sit today. Scientists studying the current motion of the plates project that this drift is heading toward another collision. In roughly 200 million years, the continents are predicted to collide again into a new supercontinent, a configuration researchers have named Pangaea Ultima. The formation of Pangaea Ultima would have profound consequences for life on Earth, assuming anything complex survives to experience it. The interior of a supercontinent sits far from ocean moisture. Wind systems can't carry rainfall deep enough inland to water the central regions. Pangaea itself had vast interior deserts for this reason. Pangaea Ultima would create an even harsher interior, possibly the most extreme continental interior climate Earth has ever had, with temperature swings between summer and winter that exceed anything in the current geological record. The collision of continents also drives up mountain ranges. As plates push against each other, rock crumples and rises. Massive new mountain chains would alter atmospheric circulation patterns, redirect rainfall, and change which regions receive enough precipitation to support complex life. At the same time, volcanic activity along the new collision zones would pump significant amounts of carbon dioxide into the atmosphere. This could drive a warming episode on top of whatever climate state the planet is already in 200 million years from now. Scientists also note something striking about where Pangaea Ultima would form. Projections place much of the new supercontinent in the tropical and subtropical latitudes, closer to the equator. Combined with a sun that will be somewhat brighter than it is today, that positioning could make the interior of the supercontinent almost permanently hostile to large land-based animals. Some models of Pangaea Ultima suggest that the habitable land area for complex animals might shrink dramatically compared to today's geography, confined mostly to coastal strips where ocean moisture can reach. The supercontinent scenario is distant enough that it falls outside the scope of any human planning horizon, but it sits in the timeline of Earth's story between current climate change and the far deeper future threat, the one that comes from the star this planet orbits. A threat that operates on a billion-year clock that has been running since the solar system formed. The sun is getting brighter. This isn't a dramatic sudden change. It happens on a timescale so slow that it's invisible across a human lifetime, or even across recorded human history. But it's real, documented, and has profound implications for Earth's long-term future. Stars generate energy by fusing hydrogen into helium in their cores. As a star burns through its hydrogen, the composition of its core gradually shifts. Helium accumulates. The core slowly contracts and heats up. To compensate, the outer layers of the star expand slightly and produce more energy overall. The result is a slow, steady increase in the star's luminosity over billions of years. When the solar system formed 4.5 billion years ago, the sun was roughly 70% as bright as it is today. Over those billions of years, it steadily brightened to its current output, and it will continue brightening for billions more, increasing in luminosity by roughly 10% every billion years. For most of Earth's history, the planet has managed to stay habitable despite this brightening. Early in Earth's history, the atmosphere contained much higher concentrations of carbon dioxide and other greenhouse gases, which kept the planet warm enough for liquid water even under a dimmer sun. Over geological time, carbon naturally got pulled into rocks and sediments through weathering processes, gradually reducing the greenhouse effect as the sun compensated by brightening. It was a long, slow, imperfect balance. That balance has limits, and scientists using supercomputer models have identified where those limits lead. As the sun continues brightening, Earth's surface will absorb more energy. Temperatures will rise. Higher temperatures will accelerate the evaporation of water. More water vapor enters the atmosphere. Water vapor is itself a greenhouse gas, which adds more warming. More warming drives more evaporation. The loop accelerates. At some point, the upper atmosphere becomes humid enough that ultraviolet radiation begins breaking apart water molecules. The hydrogen escapes into space. Slowly, over millions of years, Earth loses its water. A planet without water loses its ability to cycle carbon through the rock weathering process that has kept the greenhouse effect in check. Carbon dioxide begins accumulating. Temperatures spike further. This is the beginning of what scientists call a moist greenhouse, or eventually a runaway greenhouse scenario, similar in some ways to what appears to have happened on Venus billions of years ago. Venus today has a surface temperature hot enough to melt lead, thick with carbon dioxide, and completely dry. It may once have had liquid water. The brightening sun and a runaway greenhouse effect are the leading explanation for what Venus became. Earth's version of this fate is projected to arrive in roughly 1 billion years, though some models suggest the first severe impacts on complex life could arrive somewhat earlier, within several 100 million years. 1 billion years is so far beyond any human frame of reference that it can feel irrelevant. But the mechanism matters because it's the same mechanism, solar energy interacting with atmospheric gases and water cycles, that makes current climate change possible. The physics is the same, only the timescale differs. And the end state of that mechanism, what happens when the process fully runs its course, is where the oxygen disappears entirely. Humans need oxygen to survive. That seems obvious. What's less obvious is how close to the edge the oxygen supply actually runs, and what it takes to maintain it. Earth's atmosphere is roughly 21% oxygen. That level feels stable and permanent, but it's maintained by a continuous biological process. Living things, primarily photosynthetic organisms like plants, algae, and certain bacteria, continuously produce oxygen as a byproduct of converting sunlight and carbon dioxide into energy. If that production stopped, atmospheric oxygen would eventually be consumed by oxidation processes and deplete over geological timescales. The oxygen we breathe has been produced and replenished continuously for roughly 2.5 billion years. It's not a given of the universe, it's a product of life, and as the sun brightens, the conditions that allow photosynthetic life to thrive will deteriorate. Here's the specific mechanism scientists have mapped out. As the sun gets brighter and temperatures rise, plants face increasing heat stress. But more critically, the carbon dioxide level in the atmosphere becomes the limiting factor. Plants need carbon dioxide to photosynthesize. As the planet warms, the silicate weathering process, where carbon dioxide reacts with rock and gets drawn into the ground, accelerates. Carbon dioxide levels drop. When carbon dioxide in the atmosphere falls below a critical threshold, most land plants can no longer photosynthesize efficiently. C3 plants, which account for the vast majority of plant species on Earth, including wheat, rice, most trees, and most grasses, shut down when carbon dioxide falls low enough. The exact threshold is estimated to be somewhere around 150 to 200 parts per million. Current atmospheric carbon dioxide sits around 420 parts per million. As land plants begin dying off from carbon dioxide starvation, oxygen production from those plants stops. Atmospheric oxygen begins to fall. Slowly at first, then faster as the remaining plant life collapses further. Scientists modeled this process using advanced simulations and found that the transition, once it begins in earnest, could happen relatively quickly in geological terms. The models project that within a geologically brief window after carbon dioxide drops below the plant survival threshold, atmospheric oxygen could plummet from 21% to near zero. Complex animal life, including anything requiring the oxygen levels humans need, would disappear. The planet wouldn't become lifeless immediately. Microbial life, particularly anaerobic organisms that don't need oxygen, would persist. Earth might return to something resembling its state before the Great Oxidation Event 2.5 billion years ago. A planet with living microbes but nothing complex. Nothing with a nervous system, nothing with eyes, nothing that would recognize itself as alive in the way we understand the word. This process is projected to complete roughly 1 billion years from now. Some models suggest the first significant oxygen decline could arrive several 100 million years earlier. For perspective, complex animal life appeared on Earth roughly 540 million years ago. If the oxygen timeline holds, complex life has already lived through more than half of its total available window on this planet. That window is closing. Slowly, measured in geologic ages, but closing. And while 1 billion years sounds like it erases all urgency, the connection between this long-term fate and the present crisis is not as distant as it appears. Earth has a lifespan. Every planet orbiting a brightening star does. Scientists who study the deep future of planets call this the biosphere lifespan. It's the total window of time during which conditions on a planet can support complex life. For Earth, the window is finite, and it's moving. The oxygen collapse described in the previous chapter represents the natural end of that window. 1 billion years, give or take, before the combination of a brighter sun, declining carbon dioxide, and collapsing photosynthesis closes the door on complex life as we know it. But the more immediately relevant version of this idea is about understanding where Earth sits right now in its own life story, and what that context means for how we should think about the present moment. Earth formed roughly 4.5 billion years ago. It took about 500 million years before conditions stabilized enough for the first simple life to appear. Another 2 billion years passed before the atmosphere oxygenated enough to support complex cells. 540 million years ago, complex multicellular animals emerged. Dinosaurs appeared roughly 230 million years ago and dominated for over 150 million years. Humans in our current form have existed for roughly 300,000 years. Humans have been industrial, burning fossil fuels and reshaping the planet at large scale for roughly 200 years. 200 years on a 4.5 billion year timeline. That 200 years has already shifted the trajectory of the biosphere enough that scientists can measure it from space. Here's what makes the countdown clock concept important rather than just interesting. It reframes the stakes. Earth's window for complex life is not infinite. It has a natural closing date. And the question of how humanity uses the remaining window, whether we protect the systems that make it livable or destabilize them further, is a question with permanent consequences. If Earth's biosphere has roughly 1 billion years left under natural solar brightening alone, then the present crisis is an acceleration of the end. Human activity is pushing Earth toward less habitable conditions at a rate thousands of times faster than the natural solar process would. The solar threat arrives in 1 billion years. Some of the tipping points scientists are watching could arrive within decades. The countdown clock isn't meant to provoke despair. Scientists who work with this framework consistently say the opposite. The fact that complex life has a finite window makes every portion of that window more valuable, not less. Protecting the conditions for complex life to continue isn't a luxury or a policy preference. On the timescale of Earth's history, it's the defining task of the only species aware enough to understand the stakes. There's also a humbling quality to the long view. The systems that make Earth habitable took billions of years to build. The atmosphere, the ocean chemistry, the soil ecosystems, the biodiversity, the water cycle, all of it assembled over timescales that dwarf human civilization by millions of times. The stability humans inherited was not free. It was a product of deep time. Understanding that doesn't make the present crisis more abstract. It makes it more concrete. Because the systems being lost right now, coral reefs, glaciers, Amazon rainfall cycles, Arctic permafrost, they also took enormous amounts of time to build. And they don't rebuild on human timescales. Before the collapse arrives, there's often a deceptive quiet, a period where the numbers look stable on the surface even as the foundation shifts. And that pattern, the calm before systemic failure, turns out to be one of the most important and least understood features of collapsing systems. Systems don't usually announce their failure in advance. A bridge holds its load. It holds its load. It holds its load. Then one day, it doesn't. The failure looks sudden from the outside. But engineers examining the structure afterward always find the same thing. Months or years of accumulated microfractures, stress points, and material fatigue that were invisible to anyone who wasn't specifically looking for them. Ecological and climate systems follow the same pattern. Scientists studying resilience in complex systems use the term critical slowing down to describe a specific signal that appears before a system collapses. As a system approaches its tipping point, it loses its ability to recover quickly from small disturbances. A healthy forest, hit by a drought, bounces back within a season. A forest near its tipping point takes longer to bounce back. Longer still. Until eventually a drought that would previously have been minor becomes the final push that flips the system into a new state. The slower recovery is detectable if you know what to measure. Scientists looking at satellite data on vegetation health, ocean ecosystem productivity, and ice sheet dynamics have found this critical slowing down signal in multiple major systems simultaneously. The Amazon is one of them. The recovery time from dry seasons has measurably lengthened over the past several decades across large portions of the basin. The forest is less springy than it was. It absorbs a shock and takes longer to restore itself. That loss of springiness is the early warning signal. The Atlantic Ocean circulation shows similar signals. The circulation has slowed compared to its state 1,000 years ago. Proxy measurements from sediment cores suggest the current system is operating at its weakest point in over a millennium. A weakening circulation is one of the early indicators researchers track before potential collapse. Here's what makes this concept particularly unsettling. A system in the critical slowing down phase looks superficially normal. The Amazon still looks like a forest. The Atlantic circulation is still moving, taps still run. Sea levels are only a few inches higher than a century ago. Someone not paying attention to the rate of change or the resilient signals would see a world that still appears broadly functional. That's the deceptive calm. The system is still performing, but it's lost the cushion that allowed it to absorb disruptions. The margin between current state and collapse has narrowed, sometimes dramatically without the change being obvious from the outside. Scientists who study this phenomenon often use the analogy of a lake. A healthy lake can absorb agricultural runoff for years, filtering it through plant growth and bacterial action, with no obvious visible degradation. Then, one summer, with slightly more runoff than usual, algae explode across the entire surface. The lake chokes, fish die, the transparency of the water drops to near zero. The lake has crossed a threshold, and here's the crucial detail. It doesn't cross back. The new murky state is stable. The clean lake state was what was fragile. It only looked permanent. Multiple major climate systems appear to be in the still holding, but the cushion is gone phase right now. The measurements are there for anyone who studies them. The systems are performing, but their resilience scores are dropping year by year. This makes the next decade or two an unusually important window. Acting while systems are in the critical slowing down phase before they flip is meaningfully different from acting afterward. What daily life in a post-tipping point world actually looks like for ordinary people isn't abstract science. It's the question that ties all of this together. Most people think about climate change in terms of temperature numbers and parts per million, degrees of warming, inches of sea level rise. Those numbers are real and they matter. But they don't immediately answer the question that most directly affects daily life. What does it actually feel like to live in a world that has crossed the major tipping points? Start with food. In a world where the Amazon has flipped from a carbon sink to a carbon source, where permafrost methane is accelerating warming, where glaciers no longer reliably feed major river systems, and where pollinators have declined significantly, the global food system faces simultaneous pressure from multiple directions. Supply chains built for stable, predictable growing seasons face growing seasons that are no longer stable or predictable. Staple crop prices spike more often and recover more slowly. Hunger doesn't necessarily spread uniformly. It concentrates in the regions already operating closest to the edge: Sub-Saharan Africa, South Asia, parts of Central America. Move to water. In a post-tipping point world, multiple major aquifers are approaching exhaustion. Cities built on rivers fed by glaciers that no longer exist face permanent water stress. Governments compete more aggressively for access to the remaining stable freshwater sources. The word water security shifts from a development concept to a geopolitical one. History suggests that competition over essential resources under stress rarely stays theoretical. Then there's migration. Sea level rise combined with extreme heat events pushes populations out of places that have been continuously inhabited for thousands of years. The Ganges-Brahmaputra Delta in Bangladesh, the Mekong Delta in Vietnam, the Nile Delta in Egypt. These are among the most densely populated agricultural regions on Earth, and they sit at or just above current sea level. Hundreds of millions of people don't move quickly or easily. Migration at that scale strains every receiving region's infrastructure, housing, services, and social fabric. Insurance and infrastructure costs rise continuously as extreme weather events become more frequent and more severe. Governments in wealthy countries face the compounding budget pressure of repairing aging infrastructure faster than it was designed to age, while simultaneously investing in adaptation measures that their populations never expected to need. Here's the detail that most people don't factor in. All of these pressures interact with each other. A region hit by drought and food insecurity is simultaneously more vulnerable to political instability. Political instability makes coordinated climate response harder. Harder coordination makes the underlying crisis worse. The systems that fail aren't just ecological ones. They're social, political, and economic ones, all responding to the same underlying physical changes at the same time. Scientists studying these interactions use the term cascading systemic risks. The word cascading is important. The risks don't arrive one at a time, manageable in sequence. They stack. They amplify each other. A society managing a food crisis, a water crisis, and a migration crisis simultaneously is a society with far less capacity to make the kinds of long-term investments that would address the root cause. The post-tipping point world isn't an apocalypse with a clear before and after. It's a gradual tightening of constraints, less resilience, less slack, fewer options. The world still works, but it works harder for less, and the people at the bottom feel it first. Which is exactly why the question of what's still reversible, what can still be pulled back from the edge, is the most important question in the entire conversation. Here is what the science actually says about reversibility, because this part matters as much as everything that came before it. Some things are already locked in. Committed warming from past emissions will arrive regardless of future decisions. Certain glacier systems are already in retreat that will continue for decades. Some coral reefs that bleached repeatedly will not recover. Certain freshwater aquifers that have been over-extracted will take centuries to refill, if they refill at all. Acknowledging those locked-in outcomes is accurate. Concluding from them that all outcomes are locked in is not. The difference between 1.5 degrees of warming above pre-industrial levels and 3 degrees is enormous. The difference between 3 and 5 degrees is civilizational. Each fraction of a degree avoided by cutting emissions is a fraction of a degree less pressure on every tipping point system still operating within its resilience range. Scientists who study the tipping point thresholds are increasingly clear on one point. Most of the critical thresholds have not yet been crossed. The Amazon is stressed, but research suggests the full basin tipping point has not been reached. Greenland's ice sheet is declining, but some models still show scenarios where rapid emissions reduction prevents crossing the irreversible threshold. West Antarctica's Thwaites is in retreat, but the rate of future collapse depends significantly on how much additional warming occurs. Permafrost is thawing, but the rate of methane release scales with temperature, and temperature scales with emissions. Every emission reduction matters. Every year of delay matters in the opposite direction. Beyond cutting emissions, scientists are actively researching and in some cases piloting a set of interventions that could help. Reforestation and forest protection, particularly of the Amazon and boreal forests, could protect and restore significant carbon storage capacity. Wetland restoration rebuilds both carbon sinks and biodiversity. Changes to agricultural practices, including reducing methane from livestock and changing how soil is managed, could reduce a meaningful fraction of human emissions. Mangrove restoration protects coastlines and stores carbon simultaneously. More controversial, but increasingly researched, are direct atmospheric interventions. Carbon capture technology, which pulls carbon dioxide directly from the air, exists and works, but currently at costs and scales that make it a supplement to emissions reduction, not a replacement for it. Solar radiation management, which involves reflecting small amounts of sunlight back into space, could theoretically slow warming, but its side effects and governance questions remain deeply uncertain and contested among scientists. The window is real. It is also narrowing. The mechanisms that make delay costly, committed warming, feedback loop activation, and ecological resilience loss all operate in the direction of making each year of delay more expensive than the last. There's a specific framing that the scientists behind the major warning letters used. They said the transition needed to prevent the worst outcomes was large. It required changes to energy systems, land use, food production, and consumption patterns at a scale and speed without precedent in modern history. But they also said it was physically achievable. The technologies exist or are close enough to development. The natural systems, if protected, can support recovery. The window is not closed. What it requires is urgency matching the scale of the problem. And that brings everything back to the 15,000 scientists, the 14,000 who followed, and what they were actually asking for when they published their warnings. 15,000 scientists signed a letter. 14,000 more followed. The letters went to governments, to universities, to media organizations, to anyone who would distribute them. What did they actually want? The documents were specific. They listed interventions, not vague appeals for doing better. Rapid transition away from fossil fuels with a concrete timeline. Protection and restoration of forests, particularly the Amazon and the boreal forests of the north. Reduction of methane emissions from agriculture, waste, and fossil fuel infrastructure. A dramatic reduction in the rate of habitat destruction globally. Shifts in food systems toward less resource-intensive diets. Investment in clean energy at a scale that would genuinely replace existing infrastructure, not merely supplement it. These are large asks. The scientists knew that. They said so. They also said that the alternative, continuing on the current trajectory, would impose costs far larger than the costs of transition, just distributed unevenly and arriving mostly later, which is why political systems consistently underweight them. Here's the thing about urgency that the scientific community has struggled to communicate. Urgency doesn't mean panic. It means acting proportionally to the speed and scale of the problem. A doctor who tells you your blood pressure is at a dangerous level is being urgent. The appropriate response is immediate lifestyle and medical intervention, not alarm that paralyzes you and not dismissal, because you feel fine today. Earth's vital signs are the equivalent of a dangerous blood pressure reading. Some of them are already at the level where doctors would be recommending immediate treatment. 18 of 31 at record extremes isn't a minor concern. It's the kind of reading that gets you admitted for observation. The scientists aren't predicting the end of the world. The documents are careful about this. They're predicting the end of the stable conditions that allowed human civilization to develop over the past 12,000 years. A world that's 3 or 4 degrees warmer isn't a dead planet. It's a profoundly harder planet. Harder to feed people on. Harder to build stable societies on. Harder to maintain the kind of economic complexity that produces medicine, technology, and the systems people depend on for basic well-being. The time between now and that world is not fixed. It depends on choices made in the next decade. The emissions trajectory of the next 10 years will determine how much warming is locked in beyond what's already committed. The land use decisions of the next decade will determine whether the Amazon crosses its tipping point or pulls back from it. The policy decisions of the next decade will determine whether Thwaites continues its current retreat or accelerates. None of those outcomes are predetermined. The 15,000 scientists who signed the 2017 letter and the 14,000 who signed the follow-up weren't asking anyone to feel hopeless. They were asking people to feel the correct amount of urgency. The kind of urgency that produces action proportional to the scale of the problem. They were asking because they had looked at every planetary vital sign simultaneously. They had modeled the tipping points. They had tracked the feedbacks. And from inside all of that data, they reached the same conclusion from every direction. The window is open. The window is closing. And what happens inside that window is still, despite everything, something humans can influence. That was the warning. It still is.